All right. So yeah, thank you everyone for attending the AICT evening group today. Today we have Louis Jabouri that's going to talk about compact proofs of model performance via mechanistic interpretability. So Louis completed their PhD in 2024 at Imperial College London under the supervision of Anna Karani. Their research focused on arithmetic geometry, representation theory, and number theory, with particular emphasis on the p-adic geometry of Chimera varieties and Emerton-Guy stacks. They are currently at Eluther AI, working on various aspects of AI safety with a focus on interpretability, the theory of deep learning, and training dynamics. So thanks so much for presenting today. The presentation part will be recorded and the question part after will not be. So the floor is yours.
Yeah, thanks very much. Thanks for having me. I'm excited to have a chance to talk about this work that I've been doing over the last few months. So the title of the talk is Compact Proofs of Model Performance via Mechanistic Interpretability. Is it too true to be good? And this is the question that we'll be trying to discuss and answer today. Before we get into some technical details, I would like to give some high-level view of what I will be talking about and also maybe how it fits in a bigger context. So the main paper that I will be presenting today is this paper that was published last year, which introduced this idea of using concepts from formal verification and apply them to neural networks and specifically neural network interpretability. There are some follow-up empirical results that we also be discussing, specifically, two more papers that have used this idea of compact proofs for other types of neural networks. I should stress, though, that all these empirical results are for toy examples, so there will be I will not be really talking today about language models or like some fancy result using SAE, so proving anything about the language model. And I mean, we will see why, because it will turn out to be pretty difficult. So rather, this talk will be a bit more foundational, and I will try to cover a bit and talk about what are kind of fundamental abstractions, compact proofs, and or mechanistic interpretations, and how do these relate to our interest in applying them to safety. So this may be a good chance to think about these kind of questions. So these two papers are empirical results. I will also make some references to two papers that I recently published with my co-author Kola, which are on the philosophical foundation of mechanistic interpretability, where in there we also discuss how compact proofs fit in that picture that we draw in there. All right. So what I will be talking about is this kind of spectrum, or rather like one end of it. And I think this is an image that I see frequently evoked, and then I just want to take a minute to explain, maybe like explain what this is, and then like what exactly I think we were trying to do. So typically you think about mechinterp as covering something called like the average case. So let's say you find some circuit or like some causal structure inside your model, and so use that structure to make claims or statements about neural networks and how they compute certain things. Importantly, your explanation will be always some sort of approximation. There will be some error, and you can and will not make general statements about how the model will perform in all cases, right? So interpretation usually will be some sort of limited or modular structure, and it doesn't allow you to infer something that is maybe very much out of distribution or like out of the thing that you're trying to cover. And this is obviously not so good if you want to apply mechinterp to safety relevant applications, because in these kind of situations, you have something like adversarial examples or just generally scenarios which are very, very unlikely, but also very, very bad. And these kind of scenarios is something that we would like to cover. And because they're very, very unlikely, it's not very likely that we will just get there through like some sort of sampling, but rather we would need something more sophisticated. And so then we have the left end of the spectrum, which is like dealing with the worst case. And so in this kind of scenario, we are trying to really prove things about models and get guarantees, which means we really want to have assurances of some type, which go not like way beyond the average case. We want to make statements about all kind of possible things that can happen. And so this is obviously very good if we can make it work for applications of safety. It would be great if we get guarantees. But yeah, as you will see, this might or might not be feasible. And so somewhere in between, you can think, let's make a trade-off, and somewhere in between you have ARC's agenda, the Alignment Research Center, kind of working on something in between in there. But so today's talk will be about this end of the spectrum. All right. And so there will be roughly two parts. The first part will be, really focusing on the formal proofs. I'll say what they are, give some high-level example, also some low-level example, just give you like a feeling. And then the second part, I will try to relate the ideas that I've seen to more general literature and like more general notions and problems that we see in mechanistic interpretability, and specifically with the notion of evaluating explanations. All right. So I want to start by like slowly formalizing some things, and first give some motivation for more precisely for like what kind of proof you might be looking for. And this kind of setup that I'm describing, I also took from some slides. I was inspired from some slides by the Alignment Research Center. So let's assume we have some data distribution, some model, and something that we call a catastrophe. And so here I'm assuming we already formalized what catastrophe means, which can be very, very difficult. But for the sake of this talk, I just want to assume we already did this hard part, and now we're kind of faced with the second part of this problem. So think about a catastrophe is if the model outputs the token bomb, or like if it outputs instructions on how to build a bomb. The key question we would like to know is, given this distribution, how likely is it that my model will output like such a catastrophe? And if we would have access to this number, this would be obviously very valuable. And we could try to use this in a variety of ways. Maybe it would be even great if we like can even prove that the probability is 0 in some extreme cases. But generally, we might be content with like knowing that the probability will be very, very, very low. And so, technically speaking, or strictly, you would like to have an exact answer. But as I said before, maybe like you might think this is intractable, and then you would maybe just want to estimate or try to approximate this quantity. But this is kind of the key motivation that is maybe good to keep in mind for what I'm about to say. And even though I'll not be using exactly the setup, I think this is like a good motivation to think about why we're trying to do this. So now I want to kind of prepare the stage for the paper, the compact proofs paper. And so, let's say, again, we have a model with some weights theta trained on some supervised task. We are interested in generating formal proofs of theorems of the following kind. So we want to bound the accuracy of the model on X, and we want to lower bound it. So we want to say our model is at least as good as B on this on like this set X. And there are like variants of the statements that you could be interested in proving. So the formalism is flexible enough to allow, for example, trying to prove upper bounds of the loss, or really any quantifiable metric that you have, you can reason about its bounds. And so you have to be just careful, I think, about if you want to lower our upper bound. The key point is like you always want to pessimize. But for the sake of this talk, I will at least for now keep it in this simple scenario or setup. So yeah, so the accuracy of the model on X is lower bounded by this bound. And so I want to start by giving like 2 example proofs. One is the vacuous bound. So this is the bound which says that the model will get at least zero accuracy. This is indeed not a very useful proof. I mean, it's a very easy proof, but it's also not very useful. Like you always obviously know that the accuracy will be at least 0. This is like the vacuous or trivial bound. The second bound / proof is the brute force one. So in that case, the bound is equal to the accuracy itself. So this is kind of the best bound we can get because it's like, in fact, equal. And this proof is done by running all inputs of X, saving kind of the computational trace, keeping track of what points the model gets right, what points it gets wrong, and then you just can compute the quantity from this. And so if you want to think about this on like a scale, we have the performance lower bound, and so the trivial proof is on the low end of the scale, and the brute force proof is kind of optimal. And so obviously you look at this, you're like, okay, then why don't we just always do these brute force proofs? Well, something is missing here, because in reality, the input space X will be like way too large to make any sort of like brute force, to apply any sort of brute force techniques, right? So if you just think about transformers having like some sequence lengths n and tokens which are like live in a 50,000 dimensional space, you will have way too many combinations, and so it becomes infeasible to do this exhaustive thing. And so what I'm trying to advocate here is that for a proof, and later on for an interpretation, because I will try to make the case that an interpretation is some sort of proof, or will give you some sort of bound with a proof, you don't only care about faithfulness, but you care about the second metric, namely the compactness. So better, instead of performance bounds, we want to think about a trade-off. We want to have proofs or bounds which are faithful to the model, but also ones that are compact. And so just briefly saying, compactness can be measured through like computational complexity, flops to verify the proof, or time to run the proof. So you can use like a nice definition from the formal verification literature, but I think it's, for the purposes of this talk, definitely it's fine to think about these kind of proxy metrics. And what we're only getting now is like a Pareto frontier. We want to push the frontier in the upper left direction. Namely, we want proofs which are more compact, and at the end of the day, this just means like more human understandable, but also proofs that are still close to the actual model. So we want to be as close to the dashed line as possible, and generally go up. And right, so that's kind of our goal. And so now you might ask, how do we push this Pareto frontier? How do we improve and get like better proofs? Well, the natural thought to have here is like, when we want to generate better proofs, well, we need to make use of some structure, because this brute force proof didn't really make use of the internal symmetries or like definitions, functions that the model uses. And so we need a better understanding of neural networks to generate these more compact proofs. And that leads us straight away into mechanistic interpretability. So here's our plan. Use mechanistic interpretability, generate explanations of these, generate explanations through like techniques in there, and turn these techniques into proofs to push the Pareto frontier. And so this leads us exactly to the setup of this compact proofs paper. I want you to focus for now only on the left picture. So you see the toy setup that they have there. You have the data specifically is given by a sequence of 4 tokens, and each token represents an integer between 0 and 63, one hot encoded. M is the wall-line transformer, attention only, so we have no MMLP or no layer norm. And the task the model was trained on is to predict the max of these 4 tokens. So what I did in this paper, and we will go into more details now, but like what they did basically is take this model, train it so that it performs well on the train set, and then try to interpret it using different techniques and see how they compare. And so now you can see you have the brute force proof, which doesn't use any part of the model. And then you have like the cubic and subcubic proofs, which are more compact proofs. And the cubic and subcubic refers to the computational complexity. And how do you do this? Well, basically, the idea is, let's, for example, look at the cubic proof one. You have different paths inside your model. You reverse engineer each of these parts in a modular way, and then you bound the worst case behavior of the noise, or rather of the approximation error, I should say. So for each, for example, interpret the direct path, the QK circuit or the OV circuit, and then you want to say this is bounded by some, my approximation is bounded by some error. And in the end, when I put back all these pieces together, I keep track of the noise, of the approximation errors and how they add up. And what I always have to do is I will have to always assume that the noise adds up in the worst possible way. And this is important because we want to have guarantees, we want to have proofs, we have to make this assumption. It's, at least to me, it's obvious that in practice, on reality, probably the noise will typically not add up in the worst possible way. But yeah, as I said, if you want to have these proofs, you need to make this assumption. And I want to just to give a feeling of how we can use structure to generate more compact proofs. I want to give a very low-level example. So let's assume you're like a mechanistic interpretability researcher, and you're studying the attention of this model, and you look at this, you stare at this heat map, and you're like, okay, wait. So surely this doesn't look like just a random matrix. I can infer that, in fact, what happens is that I always pay more attention to tokens that are higher. And this kind of makes sense. So what the model does, presumably, is it pays more attention to tokens that represent higher numbers. This is how it knows that this is the token that it should output. But you don't only see that. You see, in fact, it's a little bit like it's almost constant in the vertical direction. So you see that this matrix is approximately rank 1. And surely this is something that we should be able to use to kind of save us some computation, because that's what we're trying to do at the end of the day with the compact proofs. So here's the idea of how, in this specific example, you can try to do this. You first compute EQ and KE, so these two matrices, and you use rank 1 approximations of these two and multiply them together. And now you have an approximation of EQKE. And the important thing is, the upshot is you don't multiply EQ and QE directly, but you can use these lower rank approximations and estimate the errors. And so multiplying lower rank matrices is very cheap comparatively, and this is great. This is we won. Now we only have to make sure that to estimate the errors, we don't actually compute the EQKE part by hand, but we use some clever trick, which I will not go into detail. But if we can do that, then that's great. We are able to use our explanation to save us some part of the computation, where we don't need to multiply all these 4 matrices with each other. So then you see that you go from d vocab squared times d model to d vocab times d model squared. And typically, the d vocab part will be much larger than the model, and so that's very good. And so actually, what you can see now here is you have the attention part, you have this rank 1 approximation, and you can see the strict difference. So I didn't plot the approximated difference, but just the strict difference to show you that in fact the matrix is indeed almost rank 1. It's very close to that. And in this case, yeah, you're lucky in that your approximation is indeed very, very close to the ground truth, and you will be you'll be able to approximate the error in a reasonable way. Obviously, in real life, when you look at real models, it will be not that nice. Like, I don't think it will be very often the case that you will be in this kind of very specific situation or this kind of nice situation. But this is kind of a starting point, and maybe this also should tell you that, like, for more general things, it will become more difficult. And now I want to show some results. So remember that I showed you this plot of like this parameter frontier, and this is the results that I got in this paper. And so what you see like in different colors, different proof techniques, which have different complexities. So some are more compact than others. And yeah, you see like there's some sort of parameter frontier that is pushed to the top left. And one thing that's like very nice is that the brute force proof and the cubic proof are very close to each other, but the cubic one saves you several orders of magnitude of flops. And in this kind of toy example, you see that, yeah, indeed, you save. You are able to use mechanistic explanations to save you some computations. Here's
we have a question.
Yeah.
So can you give like an example of what a cubic proof looks like? Because with the example that you gave previously, I'm a bit confused.
Mm-hmm.
Yeah, if you have any.
Sure. Okay. Let's. So, and then I think the important thing to look at is the picture here, specifically the picture for the cubic proof.
Okay.
So the important thing is you decompose your model into several parts, kind of in a modular way. Yeah, like the QK circuit, the OV circuit, and you try to make these low. Like, I guess one thing you can try to do, and one good way to think about this, like, yeah, you make these low-ranking approximations. You try to understand these components as like doing something more simple than just what you would get from like using these matrices as a black box. And then you split your data set in a smart way where you don't. So the important thing, so I guess the important thing really here is when you make these proofs, you can infer statements about data points without running them through the model. I guess that's like both the beauty and the difficulty of it. So essentially, you decompose your data set into several sub-data sets, and then for each of these sub-data sets, you can make statements about how the model should behave. And from evaluating it on a few points in a smart way, you can make inference about how it will behave more generally. I think, I will say, I myself found it very difficult to actually understand how the details of this work. So, like, to get a really good picture, I'm afraid like you will have to read the paper. I think on the high level, what I can say is like, yeah, basically try to use approximations, keep track of the errors, and then make sure that you add the errors in the worst possible way to be able to get like guaranteed bounds.
Okay, so basically, like when you get like, so we have several orders of approximation of how the model works, and then based on that approximation, you can, as you said, like partition the data set into ways that make sense with the approximation that you made, and then because you already know that within the approximation you would exactly know so you approximate the model with approximate models which they're for which you can compute the accuracy within
right.
Okay, I see. Okay,
and I mean, and okay, I can say maybe one thing. In practice, what you do, at least in this paper, is the quantity you're specifically interested in is the margin. So the difference of the correct output logit minus the max logit. And yeah, this quantity, if it's smaller than 0 or greater than 0, depending on which order I set them, you know that it's going to be the correct one. And so then if your bound can show that it's smaller than 0, I think that's the correct direction, then you're good to go. And you know that the model will have to get it right. Okay. Yeah, and I mean, so and I guess like this example that I gave, just to contextualize it, this would be basically the QK circuit part, trying to use approximations for that.
I see. And so these type of proofs, I guess they depend on the specific architecture, right? Like if you change the architecture, then you would have to come up with
yeah, absolutely
yourself with these proofs. But then you don't, like, for example, for a specific let's say approximation level, you cannot know all the ways you could explain behavior of the model. I don't think it makes sense.
Right. So it's that. Yeah. It's obviously it's very dependent on the architecture and on the setup, and obviously it's also dependent on the task. If you try to prove something about a model trained on a different task, this will also go wrong. Or I mean, you will just get very bad results. I mean, the computations and the theorems that you prove sometimes will generalize to other setups. Like this kind of rank 1 approximation idea obviously is applied to this very specific setup, but there's nothing stopping you from trying to apply that to like some attention head in a different model, just like the idea of like rank 1, like using rank 1 approximations. But obviously to apply these, you will have to find that the other model you're trying to interpret is indeed doing such approximations. And I will say in a bit about some problems and like ways to extend this to other models. But yeah, I mean, in fact, it's also dependent on your interpretation. You could also have 2 different interpretations of the same model, and these might have different causal mechanisms, which would then presumably cache out in different types of proofs and bounds.
Okay. Okay, cool. Thank you.
Yeah, thanks. Okay, so that's yeah, right. So that's the period frontier that you saw for this max of 4 example. And then what we did is we basically looked at a different toy example, which was taking a neural network trained on group operations. So that's similar to this model addition setup. And so you can see in this plot, we were able to, you can see the orange dots. So each dot is one model, like with different weights. And so obviously the brute force proof will have a very good accuracy bound, but also take longer. And then you see 2 kind of clusters on the left. So our proof that we generate was faster. And then for 50%, we get a very, very good bound, which is almost true to the actual model weights. But for the other 50%, we get a very, very bad bound. So, I mean, if you really squint really hard, you still get this sort of Pareto frontier. But in this case, what I want to highlight is the compact proofs we get, like the bounds specifically for concrete weights. They can be very strict. So if you would look at if you would like study the model weights of the green dots, like mechanistically, and look at the usual metrics and statistics that you would look at, they're not that far off from our interpretation, which we call like row sets. But in some sense, this compact proof stuff is very unforgiving, because as soon as the error might be a little bit too big, it can really propagate and compound very quickly, and then can completely ruin your proof or ruin your bound, and then that makes it very useless. And so that's just like one of the example, one of the like 2 obstacles that I want to present here. As you saw, like in the as I mentioned this previously, for example, when you multiply 2 matrices in a amortized way, you have to also do the error approximations in an amortized way. And if the noise is too big, or you have too many matrices, or the matrix is too are too big, then the noise can stack up very quickly. And so in here you see different, from the max of K paper, max of R paper, you can see different strategies to approximate this noise. And so if you do if the complexity is quadratic, you get kind of decent-ish results. But as soon as you try to approximate things linearly, especially as they add up, then the errors just become way too big. And you gain 1 to 2 order of magnitudes. Second point, also as you go to more complicated models, you get more layers, and you will have to keep track of how all the possible interactions of different errors are. And so more precisely, your interpretations mechanistically usually will be more modular. So this part will be responsible for this feature, or this part will be responsible for this mechanism. But as you get more and more components, you will have more and more noise to keep track of, and because you always have to assume that things are stacking up in the worst case, this can also really shoot you in the foot and ruin your proofs. I want to present one way to try to address these issues. So one way to overcome these obstacles is step one, as I said, turn the interpretation into either a lower bound of the accuracy, but maybe you want to turn it an upper bound of the loss in this example. Fine-tune your model to minimize on the bound. So this is kind of weird. And at least when I heard it the first time, I really had to suck it in and think about what does this even mean? But the goal of this would be, because you're upper bounding the loss, the fine-tuned model will automatically also minimize the loss itself. Because as the upper bound would go up, the loss should also go. As the upper bound of the loss goes down, necessarily the loss will be at least as bad, or at worst as bad as the bound itself. So ideally, we don't have to pay an interpretability tax. But also, if you optimize on the difference of the bound and the loss, as you optimize on the bound, the difference will go towards 0, and the closer the bound and the loss are, the closer our interpretation is matching the model. And this is some ongoing work that I have, where again in these kind of thorough models, you see that sometimes it works. But obviously, this would also need to be scaled up and tried in bigger cases, and it's not so clear what will happen in that scenario. Okay, I want to kind of wrap up this compact proof stuff to then also talk about the more general picture and application to mechanistic interpretability. But the takeaway here is our compact proofs give us a way to evaluate and quantify interpretations, and importantly, both faithfulness and compactness. And if we were to live in a good world, or if life was easy, yeah, we could get rid of this exponential branching that I was mentioning. We could use fine-tuning to suppress errors. And since then we have quantities, quantifiable metrics, we can formalize these, and we can do automatic things. We can do auto-interp. And this is a general, I think, issue or thing you have to be aware of and think about. As you scale up interpretations, you will have to automate to make things automatic. And the way to do that is you need to put numbers on things, and you need to be able to quantify them. And so compact proofs are one way to see that happening. Now you might say, okay, this compact proof stuff is way too strict, will most likely not scale up, will not work for bigger models. It's way too brittle. And I will respond, look, I think I agree, and I think there's a very good chance that you are right, and I myself, I'm skeptic about how well this will ultimately go. But I believe that this will raise another important question, which is okay, if we cannot use compact proofs to evaluate and quantify interpretations, then what should we use as a metric? And I think this is a very interesting and important question that we need to think about if you want to apply mechanistic interpretability to real-world applications and at scale especially. one way how I think this lack of quantifiable metrics makes itself salient is through these pitfalls where we have interpretability illusions, or where we decompose models into where we use some mechanistic interpretability to generate explanations, but then we don't somehow try to cache it out, and we just say, oh yeah, this kind of mechanism that I'm describing here, which is like sophisticated, is responsible for the thing, and then I do some sort of interventions, or I do some work to validate it, but then at the end of the day, I'm not able to like make statements about actual actual numbers in some sense. And I think this lack of I think what I'm trying to say is like there's a problem with trying to evaluate interpretations in a principled or like rigorous way. And I think it would be very important to think about this and to come up with ways to generate such evaluation methods. And I believe when you will think about, or if you think about this, how do I actually evaluate interpretations? I think some problems that you will see that you saw in the compact proofs scenario will probably also carry over to the general problem of trying to evaluate interpretations. I mean, generally, for example, as you scale up, you will have indeed in general more components, and you will need to make a judgment or a call about how these different components and different approximation errors will compose. And you will need to think about how to put that, in a quantifiable way, even if you don't do like worst case guarantees. I think the best that we can do today is described in this blog post by Sam Marks called Downstream Applications as Validation of Interpretability Progress. And I mean, I obviously recommend reading it. I think it's I think it's articulating very well this problem of trying to evaluate interpretations and the potential problems with it. And the main gist or takeaway is that, as it says in the post, that demonstrating your insights can be leveraged to solve a problem, even type problem that no one else can solve, provides validation of those insights. So you should try to find applications of your interpretability methods that are not related to some sort of interpretability statement, and try to show that you can make such you can solve such problems. So, for example, I think this is one of the paper you worked on. Like, you can make a model unbiased towards gender, and you can use this doing like very specific interpretability techniques, and you can beat baselines, black box baselines. So it's important, like you define some black box baseline, and then you are actually able to beat it. And if you can do that, that's a very good signal that what you're doing is like good, and that you are avoiding such illusions. Okay, so I wanna wrap it up and kind of conclude and recall the main points that I tried to make here. The first one being that generating proofs can be easy, and that's like just a brute force proof. But generating compact proofs is difficult, and so this is obviously saying like we really care and should care about this notion of compactness. Generating proofs can face problem at scale. This is like this branching and like this error compounding in always the worst way. But also compact proofs allow us to evaluate and quantify interpretations, and that's very good and very useful. And generally, if we can quantify things, we might also be able to optimize them. So, for example, we might be able to make the model match our interpretation. And this was the example with like fine-tuning on the bound instead of on the loss that I gave previously. But generally speaking, evaluating interpretations quantitatively is difficult, but I think crucial to avoid illusions in like a scalable and automatic way. And this kind of downstream application, I think, is the best way to do this currently. All right, I will just leave one link to my website. So if you are curious about what in practice compact proofs look like, I did a Google Colab where yeah, basically walk you through some very simple example that I defined, and where kind of together, step by step, you try to brute force proof. You try to make use of certain mathematical structures, or like structures in the model, to generate more compact proofs. You see how the bounds vary, and yeah, what needs to be right in these toy examples for stuff to work out. So yeah, if you're interested in that, I definitely recommend checking it out. All right, I think then that's it. Yeah, thanks.
Thank you, Louis. I'll just stop the recording here.
Yeah.
So we can continue.